today, so I don't need to give you too much detail. But essentially, this small V band gives you a good metallicity indicator. So it allows us to take photometry of the bulge and therefore see more than 5 million stars in a very short period of time and decide which ones we think are most likely to be metal poor. So then we followed up these in fields across the galactic bulge over 3 years on the AAT and got spectroscopy of 14,000 stars with medium resolution at the calcium triplet so that we could determine their metallicities very accurately. And from this, we've decided to follow up the most metal poor in high resolution. Here I show you the MDF of the survey. In green is the results we've found, and for comparison, the blue is from that OGLE survey that I showed you previously. So that's what the unbiased sample in the bulge looks like. And you can see that we're really managing to probe a more metal poor component than the average. We peak at a metallicity of -1, but we have a very long tail down, all the way down to -4, for which we can look for stars that could potentially give us details of the first stars in the galaxy. So in the last 4 years, we've observed how many stars is that? That's nearly 70 stars in high resolution with different telescopes and surveys. And today, I would like to show you the results of about 50 of those that we've analyzed so far. And this, for example, is one of those 50. In fact, it's the most metal poor bulge star that we've found. It has an iron abundance of -3.94, so it's almost a UMP star, but not quite. But it has a very low carbon abundance. We haven't been able to detect carbon in its spectrum. So it actually has a very low total metallicity. Its total metallicity we estimate to be amongst the 5 lowest known. So this star is really very metal poor. Even though its iron abundance is not necessarily as low as some of the ones discovered in the halo. So this is a really good discovery, and we're really excited to follow this up. And work done with our collaborator Chiaki Kobayashi has shown that we think the elemental abundances found in this star match potentially the signature of a hypernova as the progenitor that formed the gas which this star formed from. So here you can see the elements that we measured in the star. That's shown by the black star points. And these are 3 examples of different types of supernovae which could have contributed to the star's formation. And we find that the best match is to the red line, which is a hypernova of 40 solar masses. So this is really promising work. We hope to continue looking to see what the abundances of the other stars show us. But one of the most important questions we needed to address when looking at these stars is where they actually lie most of their time in the galaxy. So I'm just going to contrast two different expressions I've had over the past 5 years. This is a common one people have said to me when I've presented our survey. These stars are nothing more than halo stars, passing through the bulge on wide orbits. You just happen to see them when they're closest to the galactic center. We don't expect them to be any different from halo stars. In contrast, from the cosmological simulation paper I showed you earlier, if you can find that stars that are more tightly bound and therefore lie closer to the bulge at all times, then you can assume that the mean redshift of star formation and the earliest redshift both shift to earlier times. So to sum that up, if we find stars that have very tightly bound orbits that stay within a couple of kiloparsecs of the galactic center, then we can assume that there is a higher chance that they formed at earlier redshifts. So really it's key to look for the orbits of these stars as well to try and determine how old we think they are and whether we expect them to be different from halo stars. So in order to do that, we obviously need all 6 dimensions in velocity phase space in order to do this. And we have the positions, the RVs from the spectra. We have distances to the stars, but determined with large uncertainties from our spectroscopic analysis, but they're still distances. But unfortunately, we don't have very accurate proper motions. The public catalogs of proper motions published to date all have very large uncertainties when it comes to bulge stars, and often large errors involved as well. And so when you try and incorporate these into your analysis, you find that your stars are more often than not, you can't even constrain them to the Milky Way, let alone the galactic bulge. But we did do some digging around. Obviously, this will all be solved with Gaia, which Andreas will tell us more about this afternoon. But when Gaia comes along and gives us proper motions of all these stars, then we'll have a much better idea of what they look like. In the meantime, we turned to the OGLE Survey, which has been observing the galactic bulge region of the sky for more than 15 years now. And so they have a long baseline and have been getting proper motions of many stars. We found that 10 of our stars fell in fields that they covered. So we managed to derive orbits for just 10 of our 50, which is a good start and gives us some idea of what we expect the orbits of the whole sample to be like, but obviously is only a start in that direction. So here, for example, is the diagram of one of the orbits of our stars. In fact, this is the most metal-poor star I showed you earlier. So this is very exciting. We can see here that in the plane of the orbit, the star does not go further than 2 kiloparsecs away from the galactic center. Therefore, we can say, and that this is this shows you the orbit we derive for the star, but when we do a complete 10,000 realizations of the orbit, taking into account all the uncertainties on all the parameters, we find that it still stays within 3 kiloparsecs of the galactic center. So we can say that we're very much convinced that this star is a bulge star. It remains within the bulge region. Now, you may consider this to be the inner halo perhaps as well, but there's a lot of different nomenclature that you could argue about with this star. But the important thing to note is it's not on a wide orbit passing through, so therefore we expect it to be living tightly bound close to the galactic center at all times. And in summary of the 10 stars that we found, 5 were like this. So half of our sample show that they have orbits which remain in the bulge. 2 fell somewhere between the bulge and a halo. It's very hard to characterize whether we thought they were more bulge-like or more halo-like. 2 definitely had wide orbits passing through, similar to halo stars. And 1 showed up to have inconsistent parameters. So we can say that out of the 9 that we have, just over half do stay within the bulge, and therefore we expect them to be most likely the oldest stars known in the galaxy. And the best way of discovering what population 3 stars would have looked like at redshifts of greater than 10 to 15, which is really important. So, what results do we find in terms of abundances? Well, one of the things we've been talking about this week that people have been most interested in is the carbon abundances of this star. We all know now that there are 2 types of star in the galactic halo that are metal poor, the carbon normal and the carbon enhanced. Now, this just shows 2 samples of metal poor stars in the halo, in the black and the gray and purple points, and you can see that below about -2, about 1/5 of the stars lie above these 2 lines and therefore are carbon enhanced. So, sorry, what did we find when we looked in the galactic bulge? Well, here is the data from our sample. And as you can see, that all 40 stars with measurements, apart from 1 star which lies with a carbon abundance of 1 over Fe, the rest of the stars are all underabundant in carbon compared to the carbon enhanced stars. We don't find, we only find 1 single carbon enhanced star. Now, the more skeptical among you may be asking, well, there's a good number of reasons why it could be that you're not seeing carbon-enhanced stars. This doesn't necessarily mean it's endemic in the population. So, what reasons can we come up for us not seeing no carbon-enhanced stars? The first one could be that they're on the RGB, and therefore, when stars are on the RGB, they often deplete some of their carbon in the upper layers with CNO mixing. It gets turned into nitrogen. Fortunately, corrections for that sort of effect have been published by Placo in 2014, so we could apply those to our stars. So if this is the plot I just showed you a second ago. If I now apply the corrections that we derived from the paper for all the stars based on their stellar parameters, this is what happens. There's a slight shift. You can see that the stars that were most underabundant in carbon have moved up into the pack with the rest of them. And in fact, we now have 3 stars over the blue line of carbon enhancement, although 2 of them are only just carbon enhanced, with 1 being properly above carbon over Fe of 1. So you can see there's a slight shift, but still essentially the majority of the stars are carbon normal. So what could be the second reason for this? Perhaps, as has been suggested by people, the Skymap selection on photometry is biased against carbon-enhanced stars. Now, this is a legitimate question. Perhaps the photometry of the V-band, where the metallicity indicator is taken, is affected by the carbon molecules in that region, and therefore you are biased against those types of stars. Now, some people have done some work into looking into this. For example, the Halo Skymap search has asked this question and found that actually the percentage of stars they found that are carbon-enhanced is almost identical to the literature. Now, they do note that the most carbon-enhanced stars, those with carbon abundances of 2, 3 above solar, were not found within their survey. So perhaps there is a bias against those. But our survey in the bulge was done differently from theirs. So this, for example, is a photometric plot showing you the metallicity indicator. You can see the stars underneath that are colored have spectroscopic metallicities. So you can see that the most metal poor are at the top, the most metal rich at the bottom. Now, the Halo survey takes the ones at the very top, a small number of them, to be the most metal poor and follows them up in detail. In the bulge, we have a lot more stars, and we also wanted to probe all metallicities below -1. So you can see that we take stars from a huge region within here, going down to metallicities of -1, but also you can see we have stars going all the way up to solar. So while in the Halo, they're biased, if a star has a carbon abundance that's very high and therefore drops it from up here to down here, we're likely still to pick up those stars. So we estimate that the carbon enhancement a star would need to have to fall with outside of our selection would need to be on the order of carbon upon Fe of 4 to 5. So really, we're not biased as far as we can tell against this, apart from in the most extreme cases. So we don't believe that Skymap selection is what has caused this. So what about statistics? There are many Halo EMP stars. We only have, like I've said, we've only analyzed 50 so far. Perhaps it's just low number statistics. So I wanted to show you this on the plot of the cumulative frequency of carbon-enhanced stars in the Halo with respect to metallicity. And as you can see, the cumulative frequency goes up to 1 or close to 1 below -5. And in comparison, this is the bulge cumulative frequency. We don't even reach above 0.1. It's wildly different. And if you do binomial sampling of the data, if you take the literature Halo sample, select 50 stars from the appropriate metallicities of our stars, and say, what is the chance that they have the same carbon distribution as our stars, then the probability of that happening is incredibly tiny. As you can see, it doesn't matter if you use the observed carbon abundances or the corrected ones. It's still a probability of happening of 0.003%. We can really say that statistics, it's not low number statistics. We have enough stars to say that this is a real effect. So we have to accept the fact that the stars in the bulge, the metalpoor stars in the bulge, do not show the same carbon enhancements as the Halo. This is a really key point, and it's something for theorists and observers to consider. What would make this difference? Is it different progenitors at earlier times causing this kind of enrichment? Perhaps it's in the environment of the bulge, which causes different progenitors as well to cause. There are many possible theories and that we would like to consider in the future, but I'm really open to ideas from people out there as to what they think could be causing this. And this plot is just for Tim to show him the absolute carbon abundance. When I plot my stars on top of this from the paper that was published just a couple of weeks ago, you can see that our stars in green fall outside of the 3 groups of carbon enhancement, and our most metalpoor star is way below group 2. So we're pretty confident our stars are not carbon enhanced. So I'd just like to give you the summary of the talk. EMBLA has observed around 500 stars with medium resolution spectra that have metallicities below -2. So we're really starting to probe in large numbers the metalpoor population of the bulge and potentially the oldest stars of the galaxy. Half of those that we've been able to look at so far remain in the bulge with low orbital energies. And this will be something that when Gaia comes out, we'll really be able to improve the statistics on. These stars, more likely than any others, to have formed at the highest redshifts. These really do probe before the epoch of reionization, unlike potentially other population 3 stars. And there are significantly fewer carbon-enhanced stars in the bulge. So I'd just like to leave you with the outlook for the survey. We're not finished yet. We've just taken more observations this summer on UVIS. We've taken new observations in low red, closer to the galactic plane. And we've also observed 200 stars with the Kepler Campaign 9 in order to try and get astroseismic ages, to try and constrain the age of the entire population statistically. So that would be really exciting to see what happens too. So keep watching. We expect more exciting results to come. But I'd like to thank you for your for your attention.
Thank you, Louise. Other questions in the audience? Ian?
Can you tell us anything about the neutron capture elements in these stars?
Yes, I contemplated putting in some plots, but I figured I wouldn't have time to talk about too much about neutron capture elements in the stars. So we've made some initial findings into this. So far, they look very similar to the halo population. We don't find we do find a large scatter similar to the halo populations. We don't find any stars with extreme abundances that warranted looking in too closer. But certainly, I don't find any stars with barium over Fe greater than 1, for example. So I have looked into that sort of thing. We're doing some more studies into it into greater detail, but at the moment I would say that there seems to be signs that there has definitely been R-process enhancement, but I am yet to find any S-process enhancement in the stars we've looked at. I've got a master's student working on this at the moment, so hopefully we'll get some more results for you in the near future.
Andreas?
Thanks for an exciting talk, Louise. Rafaela told us earlier this week that the carbon normal EMP stars are not the normal second generation stars. They are the external, I think she called them the externally enriched stars. Does that make sense with the fact that we now find them in the bulge?
I'm not sure that it necessarily does. I've heard conflicting talks this week about whether that having the carbon enhancement makes them true remnants of the population 3 stars or not. I think it is definitely true that the environment these stars formed in would have been much busier than that of the halo EMP stars. And so it is, I presume, less likely that the stars we find will have been influenced by just one supernova. That therefore may influence the kind of patterns that you see there. I thought it was interesting that, yesterday we heard the talk from Salvadorians showing that if you look in larger and larger dwarf galaxies, you expect to see lower fractions of carbon-enhanced stars. Perhaps this is the ultimate extension of that idea. It's one theory.
You have another question?
If you can wait 10 years, the W1st microlensing survey will be looking at the bulge over the course of 6 years, and they think that they're going to be able to get parallaxes and proper motions. So you might check where they're looking in the bulge and where your stars are.
That would be very interesting. I certainly hope to still be around in 10 years to look at those results. I think that will be key in constraining those stars that are most tightly bound. I think we're pretty certain that the proper motions from Gaia will be enough to tell us whether the stars are bulge stars or wide halo stars passing through, but the errors involved from the distance of the bulge mean that we won't be able to tie down the precise details. So that sort of thing will be really exciting.
A question from Andy?
Thanks, Louise. This was a really good talk. I just wanted to make one point, which I'm sure you already know what this is. The carbon-enhanced fraction in the bulge, I think it's still really, really early to be able to say it's because the selection function from the commissioning data is really difficult. And a comment on that is like, from our infrared selection, we already know that we are definitely biased against carbon because we select on carbon. But we've already found extremely metalpoor stars in the bulge that are carbon enhanced, so I think it's still a little bit early.
So even though you're biased against, you've still found carbon enhanced stars in the bulge?
That's right, yeah.
Do you know sort of what number?
Of order a few, and we have, but it's still early days because we haven't analysed everything yet.
Yeah. So I know that, for example, there is one published in the literature by Andreas Koch. He found a Kemp S star. So there is small numbers. Like I said, we found one ourselves. So I'm not saying there are definitely none, but I do think we have looked into the issue. I mean, you're right. We can't constrain the selection function of the commissioning data from Skymap at all. I think that's almost an impossibility at this point from the data that we used for the survey. But we can rule out, apart from at the most extreme levels, the idea that carbon enhancement was biased against it. We certainly we're not finding stars with carbon over Fe between 1 and 2 or 1 and 3 at anything like the same levels as in the halo. So.
Okay, a final question here from Tim.
Yeah, I think you hit on at least the right direction to go with your last suggestion. The bulge is a special place. A lot happens beyond carbon production, probably basically at the same time or very similar time. And so those stars of absolute carbon abundance, which are just sort of shifted in Fe over H, which you showed, I think it's very likely that the carbon production mechanism that's associated with the group 2 carbon stars has nothing whatsoever to do with the Fe. That the Fe is being produced by other sources.
Let me go back a second.
And
see what you're
right,
saying.
you look at that diagram. Yeah, exactly. So in fact, I mean, you obviously see that correlation in group 2. That when you look at what the progenitors are likely to be, those are very likely the faint mixing and fallback supernovae. They produce some iron, but not a lot. And other iron sources in the environment, certainly in the bulge, can pump up the iron. And so I think that we have to give serious thought as to how, going forward, we talk about carbon enhancement as opposed to sticking with the ratios. The ratios were useful while we were looking for them. Now I think we understand something more about the origin, and this is a great probe of what happens in the bulge in perhaps the most extreme cases. These I would call carbon intermediate metalpoor. I mean, 0.5, that's a factor of 3. Factor of 3 is big.
I agree in the sense that you're right. The fact that we draw a line at carbon over Fe of 0.7 is in a way, it was meaningful to start off with when we were searching for them, but now can you really say that a line between these two samples here has any real meaning? We don't see a dip, for example, in the carbon distribution function, so it could be that really is no longer a good way to talk about them. Having said that, this star here really does have, I would say it's definitely low in carbon. I wouldn't call it a carbon intermediate star.
Okay, let's thank Louise again.